This is Dan Abbott. I'm making this video for the Introduction to Marine Design program that we have at Southern Maine Community College. This is the unit on Introduction to Parametric Modeling. I'm also going to be talking about lines drawings as well. This is something I would normally do in person, and I have done it in person in the past multiple times. I will no longer be able to do that in Brunswick, so I'm making this video so someone else can use it as a way of going through the process in the 4-hour workshop. I will be pausing this video periodically for a short time at moments where you should pause it yourself in the workshop so that you can then do the access and do the project that I've assigned. So you'll be using SolidWorks, which is a parametric software that we use. Not the software that is used by large ship designers, but it's very similar to it, so that's why we're using it. So first, you're going to be on the virtual desktop. Virtual desktop looks like this. Let me just minimize things here. Virtual desktop looks something like this. There's an image of Spring Point Light, which is on our campus in South Portland. You won't have nearly as many icons on your desktop because this is my desktop. So you won't see an icon over here for SolidWorks, but you're going to need to use SolidWorks. So once you get to the virtual desktop, go to the run window down here, start typing SolidWorks, and then select the app. Yours may say SolidWorks 2024 by the time you do this, might even be 2025. Right now it's 2023 that we're using. The SolidWorks program will look like this, although because you'll be running it for the first time, you'll get a dialog box asking you what you want to use for units. You can select whatever makes the most sense to you. I normally draw in millimeters, but the alternative is drawing in inches, and you'll be able to change that, and I'll show you how to do that as we go through. The other thing I want you to open is this PowerPoint that I've turned into a PDF file in this case, that I'm going to use to organize the workshop. If you go to the File Manager, and then you go and find, and you might have to open up this, you might have to open this up because it's actually a mapped network drive. You may have to pull this over here to find it, but it's the resources $, student files, and then R:, in parentheses, which is the drive letter that I've mapped to that resource, which is simply a folder. When you open that up, if you scroll down, you'll find a folder called BIW. You open that up, find a number of things here. The thing you need right now is something called Lines Drawing, Ship Modeling, Rev 04. And we're going to open up the PDF file, which is what I have open. In fact, it'll tell me that it's already open since I've already got it open. So it looks like this. You'll also need to get access to a couple of folders that are on here. And the folders that are on here under BIW are under the SolidWorks folder. If I open up the SolidWorks folder, you'll see there's something called Assembly Questions, Caster Parts, Loft Exercise, Toggle Clamp, and I'll be going into some of these at least. There's also a copy of this PowerPoint in there. So let's just start with this notion of contour line, because it's going to be critical when you start looking at drawings of ships that you understand this notion of contours. So this is a simple hiking map, and that hiking map shows you all these lines here representing contours, and those contours are generated by taking an image that's 3D and then slicing that three-dimensional image at increments that are consistent. And then the edge of what you see after you've sliced it will give you a contour line. So if we look at this, right here it says 1,000. That means that that particular contour line is 1,000 feet above sea level. Over here you see one that says 500. And the key thing to recognize here is that these contour lines are used because the shapes you're looking at are so irregular that there's no way that you could use straight lines. This is a series of hills. So these are all horizontal planes, and that's comparable to what are known as water lines on a ship design. And like the contour map here, if you notice what the lines are really close together, that means it's changing elevation really fast. So if we were to go in here, a little hard to read that number, but if you were standing right here and wanted to get up here, going straight up would mean a very steep climb. be a longer climb to come this way and then gradually get yourself up there, but it would be a lot less work. So that's the notion of a contour map, and you'll see these as well on nautical charts. So here's a nautical chart. This is Portland Harbor. The contour lines here indicate depths of water, and you can see a little more clearly here that you have a 1 foot depth here. When it gets up to 6 feet, you get a contour line with the number 6. When it gets up to 12 feet, you get a contour line with the number 12. 18 feet, the number 18. These are based on fathoms, which is a 6 foot depth measurement. And so like the contour map for hiking, if you see a lot of these lines close together, that means that it's getting shallow in a hurry or less shallow in a hurry, depending on which way you're going. So that's the key thing to understand. Let me just bring this back. The key thing to understand when you're looking at a lines drawing, and a lines drawing looks like this. Now this is a very simple boat hull, and that simple boat hull uses orthographic projection to represent, looking straight at a hull, represent that hull. So over here you have a shear plan. The shear plan will be the equivalent of a front view in orthographic projection, and that shear plan has lines representing contours in the same way that the contour map did, because the side of that ship, and in this case it's a boat, but the side of it changes shape as it goes down from the top to the bottom. At the top you have a half breadth plan. The reason it's a half is because traditionally these were done by hand, and since a boat of any kind is symmetrical side to side, it was not considered necessary to draw more than half of it from the top view. So you have a front view, you have a top view. Over here you have what's known as a body plan. The body plan represents a right side view and often a right side and a left side view, which would be the bow and the stern of the vessel. Now again, this vessel is a boat that's fairly simple. If we look at something, you can see what this is. Okay, molded plans, the outside's the frames, the inside of the shell. That's a particular kind of plan to show you what the shape of the hull is. And the body plan is a right view if you're looking at orthographic projection. Profile is the front view in orthographic projection, and that's known as a shear plan. And we'll see in a minute it has ordinates or stations. And then the half breadth plan is the top view looking down at it. Here's a 3D model from a program called Delft Ship that shows the idea. If you have this ship and you start slicing it, and you notice what I've done is sliced a little bit off one side, then I've moved it in a little bit, then I've moved it in a little bit. The resulting profile of that slice becomes this. Now this is known as a shear plan. It's not the same vessel, by the way. This is known as a shear plan, and this shear plan has what are known as water lines, and the water lines are right here, and then you have above the water line. So the water line and down has these little increments, and they're equivalent to a coordinate plane or a coordinate system like the Cartesian coordinate system, where the water lines going up would be the equivalent of the y-axis, and then you have these station lines coming down like this and going across. And those station lines would be the equivalent of an x-axis. And like the coordinate system in the Cartesian system, these increments have to be the same. And the idea is to identify locations along these various contour lines where these two lines intersect or come close to intersecting, so that you can then generate a boat hull. Either, in this case, we're going to be doing it with a computer, but in the past it was done by drawing these things out by hand and then placing them in a loft, and then the loft was used to lay out the plans so that then the boat itself could be built. The word loft becomes important in computers because that's a technique for creating 3D models when you start looking at parametric modeling or any kind of 3D modeling. So now the top is a similar kind of thing. If you have, again, this goes back to that first ship. If you start slicing it and going up, as you go up, the outline changes and gets larger and larger. Looking straight down at it, this is the equivalent of doing that on a different vessel. And these, again, are matching up with water lines and matching up with stations. And from the top, you get the same increments as you do from the shear plan or the body plan, so that you can generate what's known as a table of offsets. So here's another example of this would be a body plan of cutting a boat or a ship and then moving down through. And again, each of those contours changes in shape and size as you go from one end to the other. And that would be your body plan right there, and those are those changes. In this particular case, this body plan is a combination of the stern view, in other words, the left view, which is normally lower than the bow. Normally, I say. Sometimes it's virtually the same. But in most vessels, the stern is below the bow, though the bow in this case is higher. And again, it shows you the water lines, and at least it shows it here, but it also shows you these lines coming up and down, the X and Y types of axes, in order for you to match them up with the shear plan and the half-breadth plan. So here's something, again, generated by Delship, and it just shows you what these ordinates or stations are called. Some people call them ordinates, or some references do. But station lines is what they are, and again, they're just slices like this is a big loaf of bread, i.e. it looks like this. Now that's a 3D model, which you don't use for most technical work. You'd use something like this instead. So here we have, looking straight down at it and then looking at the shear plan. The reason why the front or the shear plan and the top are reversed is that this Delship program was developed in Denmark, and they use first angle projection instead of third angle projection. But now, just kind of come down through. Yeah, don't worry too much about the diagonals. That gets more involved than I want to get here. But for that particular ship, you now have the shear plan, the half-breadth plan. In this case, the stern and the bow are on opposite ends, but they're put down here because there's no room on a sheet of paper to put them here. And this is a particular type of ship where the stern and the bow are essentially the same height. But all these contour lines represent the view, looking at it from the bow, looking at it from the stern, looking at it from the side, or in this case I call it a front view, and then looking at it from the top with half of it cut away. And then offsets are simply a series of numbers that are generated to identify locations on each of these lines, and you end up with what's called a table of offsets, which is a bunch of numbers like this. You're not going to have to do that. Certainly you're not going to have to do that in this workshop. This is a case where now a computer will generate the table of offsets for its creation of the geometry involved. This is just, I don't want to get as involved as I have in the past with this, but this simply shows you how these table of offsets work if you wanted to go back and use this as a reference. And then here you have coefficient examples that have to do with how a vessel's hull will move through the water. Again, for the purpose of this workshop, this is not important to you. Alright, so now let's talk about three-dimensional modelers. Three-dimensional modelers used for shipbuilding, well, some of them are not necessarily three-dimensionals. So let's simply talk about computer-aided design in shipbuilding. There's a difference between what I refer to as geometric and parametric modelers. Geometric modelers, and AutoCAD is an example of one, used primarily for two-dimensional drawings, and they just essentially create geometry, and that geometry represents whatever you think it represents. So you draw a circle. That circle might be a hole of some kind, it might be a pin of some kind, it might be a large pool, it might be a tiny hole in a mechanical part. It's whatever you call it and whatever you put the dimension on to make it. AutoCAD is a 3D modeler, but it doesn't get used generally for things like ship design except by a program called Ship Constructor. We'll talk about that next. And it doesn't actually get used in Ship Constructor as a way of designing the ship, but again, I'll talk about that in a bit. AutoCAD is used, even in ship design companies, it is used for a lot of two-dimensional work, and that's primarily what it gets used for these days. AutoCAD is still the most widely used CAD program in the world, but it's not the most widely used parametric modeler in the world because it's only parametric to extent, and that parametric extent is only in 2D. So none of the 3D geometry that AutoCAD creates is actually parametric. But it does get used for schematics, electrical schematics, sometimes piping schematics, diagrams, flow charts, that kind of thing. So the difference between geometric and parametric modelers is this. In a geometric modeler, you're creating geometry, you put a dimension on it, you're calling it whatever you want to call it. But it is not necessarily representing a three-dimensional object. If you create a three-dimensional object in AutoCAD, the dimensions themselves do not drive the geometry. In other words, if you make a cylinder in AutoCAD by creating a circle and extending it a certain distance, the dimensions you put on it will represent the dimensions you use to create that cylinder, but you can't change the dimension and then have it change the cylinder's dimensions. Parametric modelers use parameters that are dimensions and relationships and mates in order to define three-dimensional geometry that can be changed by changing the dimensions themselves. And we'll see that in a minute with SolidWorks. Ship Constructor is a shipbuilding program. It is used primarily for commercial ships, but the military is kind of pushing the possibility of using it. So shipyards are put in a position where they may have to change the software they use for designing ships for the military, and they have to probably adopt Ship Constructor, or may have to adopt Ship Constructor. There's a move right now to get all the shipyards that do military ships for the United States to use the same computer-aided design software to design those ships. And the options right now are Ship Constructor, CATIA, Pro-E, and several other large, NX is another one, but there's several other large, very robust 3D parametric modelers. Ship Constructor is really a parametric database. AutoCAD is used by Ship Constructor to generate a 3D model to represent it graphically, but it is not used to actually design the ship. But again, it's primarily in the past been used for commercial ships, and we're going to see an example of that in a minute, or a few minutes. But military ships are being designed by Ship Constructor more often, and it's quite possible at some point that the military will simply require shipyards to use it. CATIA is a very robust parametric model that can model complete ships. It's very expensive, and the version of CATIA that's used for ship design at Bath Iron Works is a specialized adaptation of CATIA that was generated by the company, and that's through the relationship with Bath Iron Works and CATIA. It's manufactured by Dassault. Dassault is a French company. Dassault initially started CATIA as an airframe aeronautics CAD program for designing airplanes. It's also the same company that makes a program called SolidWorks. CATIA requires extremely powerful computers and is also very expensive, and it's also a little harder to learn. Therefore, we don't use it at Southern Maine Community College. It's just too expensive, really. SolidWorks, though, is a mainstream parametric modeler, and that is very similar to the way CATIA works, but it's designed for smaller projects. And most projects are much smaller than a ship. That's extremely complex. That's about as complex as a parametric modeling project gets. Even more so than standard building software, because a ship is essentially a big building with very special requirements. One, that it can float, but two, it doesn't have flat walls. It doesn't, it can internally with bulkheads, etc. But designing a ship requires a much more robust piece of software than designing a building. So we're going to use SolidWorks to represent the tools in parametric modeling, all of which exist in every parametric modeler. SolidWorks is the most widely used mechanical design program in the world, and again, it's also manufactured by Dassault. So what I want to do next is have you take a look at a complete, well, it's actually not complete, but it's somewhat complete ship model. This is a commercial ship. It was designed using Ship Constructor, and the company that makes Ship Constructor provided me with this model. It's not a military vessel. It's not as complete as a CATIA or another model would be when it was at its end. We're going to look at it using a program called Navisworks, which is not a CAD program. It's actually a program used for somebody that wants to go and view an existing model that was done in virtually any CAD program, but it's made by Autodesk. I'm going to obscure in the video when I produce it both this link and the password, because I'm going to put this on my YouTube channel, and Ship Constructor did not want me to share this generally, so you'll have to get both the link and the password from whoever it is that's managing this. However, you will see this when you open this file yourself, and you'll be able just to click on it. So what I'm going to do here is to open this up. But again, it's going to be obscured in this video because. So if I open this up like this, and it goes and asks me for a password, you type in the password, and then it's going to take a little while for it to actually display. But when it does, it will look like this. But again, this is a commercial, it's a container ship. It has a bow with a helm in the front. So all the superstructure is up front. Oftentimes it's in the stern on a ship like this. And I'm just going to pause my video until it loads. And there it is. So I'm just going to have you play around with this. So at this point, whoever's overseeing your workshop, at this point, they should just pause this video. Or if you're watching it yourself, you can pause this video while you go and then take a look at the ship itself. A couple things I'll just point out. You have saved views if you want to, but if you go to Model Browser, you'll notice there are a number of other views as well that have been saved. And right now, you're looking at all of them. You can turn those views on and off. In fact, if we do this, everything goes away. But you can turn them on and off, individual views. But what that means is not a view so much as where are you looking at it from, but what are you looking at. So if we say, let's take a look at this one. This is all the plimsoll depths that are here, and what it does is isolates them so that if that's what you want to work with, you don't have all the rest of the ship getting in your way. So it does look like there's a few other, no, that's not. So the only thing you're gonna be seeing here is right here, but if you keep going down, you can see like the skeg. Okay, so this skeg bottom. Interesting. I wasn't expecting that. Oh, I see. Yeah, that's the skeg bottom. It's at the bottom of the ship, and that was one of the plates that holds the skeg on. But these are individual pieces, and you can see if you're trying to work with any one of these individual pieces, how much harder it would be if you didn't have this tool. Come back up here, you see the whole ship. Go to the home button, you go back. That's enough for what's happening up here. So down below, you've got some tools for taking a look at this. A couple things that you have for tools. We have a pan and zoom. That just means you can go back and forth like this, but you can also do that using the mouse by pressing the middle wheel down. Again, zoom. If you move your wheel in and out, you'll be zooming in and out. But one of the interesting things you can do here is to pick first person. Orbit just moves it around. Again, if you put the left button on your mouse down, you can also do an orbit. So you don't really need those tools with most mice. So what you can do though in first person is this, and it gives you some of the tools when you pick it. Teleport and look around. Those are the two things you're likely to use. Teleport means if you'd like to look, say from the deck, you double click here, it shows you what it looks like from there. Then you can go zooming in and out. You can move this around and look up and down. This is all orbiting now. So you can really get a look at what the ship looks like. You can also, when you're done, come back, go back to the home, if that's starting. You can also get down inside the ship. So if you look at first person, it's always doing that. So if you go down kind of in here someplace and double click, you notice now you're inside the ship. It's not quite. Let's see. Down below. Okay, that's still on the deck. If you zoom when you're on here, if you really zoom in, get a look at it like that. Do a little panning here. I'm setting this up so what I can do is see what it looks like here. Now I'm going to zoom in till I'm right inside the ship, and then once I get inside the ship, I'm going to do the first person. Double click here with the teleport tool. And now you're inside the ship and you can look at it around at it here. So I think we're in the galley before. You can see you got to be a little bit careful how you do this, but here we go. So now you can see, you can actually do a walkthrough with this thing. Go inside, take a look at the piping, take a look at the structure. You got gusset plates for here, for instance. So if you want to see where gusset plates are used to strengthen the ship and what they look like, and those individual pieces, of course, have been modeled individually as parts. So when you want to go back, just go back to home like this, and then you can put yourself in a different position. Suppose you wanted to be up at the, suppose you wanted to be here in the wheelhouse. Now, in the wheelhouse, you go and look like this. There we go, like that. Then you can use, we're looking at the stern now, you can turn yourself around by pushing the left button down. You can kind of go in like this. So it gives you a tool that allows you to look around and see what's going on. Now the other thing, two other tools here that are useful. One of them is the section tool. Section tool allows you, suppose you want to break this in and take a look at it internally. This is on the x-axis, which would be the shear plan axis. But you notice going back and forth, you can open this thing up and take a look inside. Do it on the y-axis as well. And if you're looking x, I said that was the shear. The x is along the shear line, but if you were using it the way I just did, you'd be looking at it from the bow or from the stern. So here, there's your y-axis that allows you to look inside that way. And then the z-plane up and down, that allows you, you can see it's already down, that allows you to cut parts of this away and then take a look at it. So you can see what's going on here as well. Now the other thing you can do though, is you can do something called an explode. Where you say, what I'd like to do is to pull this ship apart. And you're pulling it apart like that. Now you can see all of the various pieces that are used to make this. And if you want to get a sense of just how complex this is, really pull this out. Go and do a fit on it. And you can see there's a lot going on with one of these ships. So no one person designs a whole ship. So what I'm going to do here is just to go and look around to get a sense of what's there. If you've already gone through some of the work with Vince, then you understand what many of these parts are called. You understand the mechanics of the ship itself, so you can go and find some of those things here. That's enough for this, so I'm going to close it. I need it open. Now, this shows you some of the viewing, some of the things I just did, exploded views, walking around. Now, this is actually a view from Ship Constructor itself of a vessel, but Ship Constructor is not a piece of software that we have loaded on the computer, so you're not going to be able to use it anyway. I just wanted to show you what it looked like. And in fact, you'll notice that the big A stands for AutoCAD, and it's an AutoCAD 2021 educational version. I created this in Ship Constructor and then opened it up here. But it's not, again, it wasn't something that was actually created in AutoCAD. You create it as a database for the various parts, and then they're displayed for you in AutoCAD. This is a torpedo recovery vessel, and this is the only military vessel that I could get access to the plans for because it's been retired. So the Navy has made this part of the public domain. And the reason I did this is because I wanted to show you what at one time were the required lines drawings to create something like this, which is far simpler than anything that is now being built for the military. Its purpose in World War II was to recover dummy torpedoes that were used for torpedo practice by submarines. And they would do the practice with it, and then they'll be at the bottom on the ocean floor. This vessel was designed to go and drag for them, pick them up, and then put them back on deck, and then reload them onto the submarines. So the reason I did this again is that I also have a complete set of the drawings for this. And if you go back to the BAW folder, the TWR drawings, these are TIFF files of all the drawings used that I, again, got from the Navy. And any one of these, if you open it up and look at it, you will see a drawing that was done by hand. Okay, these are tables and charts, also done by hand, by the way. So not as interesting. Let's go back and find something a little more interesting. All right. Oops. All right, so I'm back in that folder. Look up near the top a little bit. All right, so this is, again, this is one particular part. Actually, it might be two parts. Yeah, a little bit of an assembly over here. And this is all hand drawings, and you can tell when you look at that. It's all hand lettered. The drawings were done by hand and then scanned. This is how ships used to be designed, and very much a very involved process. Oops, I don't want that. I want to go back to this. I might have closed that accidentally. Yes, I did. All right, let's go back down. So we'll come back down here, and when we get down here, okay, so that is a partial plan for that torpedo recovery vessel. Now, the torpedo recovery vessel was also something that was created in CATIA, and it also has been created in Ship Constructor, and it's been created in a number of other programs because it's the only public domain military vessel. So it was created as for training purposes. But whenever you're building something this complex, you have to have a means of managing each of the files used to represent it. So these are computer-aided design files. And from this point of view, these were parts that were actually made in CATIA. So in this case, and I'm not going to go through all of this, but there was primary structure. That means what's the ship hull itself. We got the ship expansion, or shell expansion is the side of the hull. Inner, bottom, and first platforms are the decks. The skeg is the part that goes the length of the ship in the bottom. Longitudinal framing goes the length of the ship. Transverse goes side to side. And that's just one example of individual categories. But the overall larger categories are primary structure, the hull, the frames, etc. Secondary structure, the superstructure, the parts that go on top of the decks. Foundations are things that hold things like large pumps, electrical devices. Tanks carry water, waste oil, that kind of thing. Machinery is all about propulsion, so the rudder, the prop, the engines, the motors, whatever's driving this thing. Outfitting is the things you need on every ship to get it around. In this case, it was torpedo handling and ladders. Piping is how you move various things throughout the ship. In this case, fuel, water, air, hydraulics, sewage, and then HVAC. HVAC is, obviously the control of the heating, ventilation, and air conditioning is what that stands for. So it's all things having to do with heating. Air conditioning on that torpedo recovery vessel, very unlikely. And then electrical, all the things required to make the part run. This is actually from a CATIA file that I got of the torpedo vessel, and this is a better idea of just how complex and how much the modeling would have to take into account. So unlike the model we looked at from Ship Constructor, which had some piping but not much, you can see this has all the various equipment in here. The piping is much more complete. And also, this is the galley. So, this is one of those things where you have all the needs of a building, for housing, for eating, for cooking, for sleeping. All those things have to be in a ship. And you can obviously put bulkheads and dividers in here, and those are flat, but much of the ship itself is not. That's just one assembly from the torpedo recovery vessel. It's the bow thruster, the part in the front that can put water out to the sides using a prop and allow you to turn the boat at the bow much more readily. And that assembly, that sub-assembly, consists of those individual parts. So we're going to be doing things like that with SolidWorks. So let's start. I'm going to have you do some work with SolidWorks now, and I'm just going to give you a demonstration of how I want you to do it. But there are multiple ways to create solid models in a parametric modeling program. And extrusion is the most common, or one of the most common. And it simply requires that you take a shape and you move it through space. I use this as an example. If you're putting toothpaste on your toothbrush and you squeeze it and move it, you're creating a cylinder of toothpaste by extruding it through a round opening. So for this part right here, the shape was this outside shape right here, and it was extruded into that. You also have extruded cut. Extruded cut in this case was another shape, a couple of circles, that were extruded back to cut the part away. So let's just go back to SolidWorks. So what I want you to do here is this. I'm going to have you create a part, and I'm going to just walk you through a process, and it's going to be a very simple part. It'll be a cube. So you need to go to New. When it comes up, you have three types of files that all parametric software uses. One of them is a part file. One of them is an assembly file, and one of them is a drawing file. We're going to be working right now by creating a part file. So those are your choices. Parts are individual components. Assembly is where you take all those parts and you put them together. So we're going to start with a part file. And the first thing you need to decide is, are you drawing in inches or millimeters? You're not likely to draw on anything else. The lower right hand corner of the screen down here, MMGS. Let's see if I can use a magnifier on this. We're going to find out. Sometimes the Windows magnifier sometimes works, and it sometimes doesn't. When we're using the virtual desktop, and it looks like doesn't is what's going to happen. Okay, well, I was going to try to magnify this area, but looks like it might. Yes, it does. So let's see if it'll work the way I want it to. Well, it's not very responsive, so, but I am able, hang on just a second, I turn something off. Alright, so if you look in the lower right hand corner, MMGS stands for millimeters, grams, and seconds, which is what I normally draw on. You can also do inches, pounds, and seconds. Don't pick centimeters, don't pick meters, but you have to pick the units that you plan to draw on. Most of you draw in inches, and that's what most of the ships in the United States are designed in, so I'm just going to pick IPS for this, and then I'm going to turn off the magnifier. Okay, so now we're making a new part. We're using inches, pounds, and seconds. Now the first thing you need to recognize is that every part file starts with 4 elements, and those elements are listed over here in this feature tree. You have a front plane, a top plane, a right plane, and an origin. It's basically the Cartesian coordinate system. You pick the origin, it's going to show you where those planes all cross. Otherwise, when you go to any one of these, you can usually see them. Why can't you see them now? Not sure. We'll find out. What we're going to do is to create an extruded boss or base, but we're going to start with a sketch. So by doing that, we're going to use on these tabs up here, which are basically, think of them as toolboxes. So the Features tab has all the tools necessary to create three-dimensional models and modify them. The Sketch tool is where you start by sketching that shape you want to extrude. So we're going to go to the Sketch tab, which just opens a toolbox. It doesn't actually do anything. You can't sketch yet. You have to tell it what you want to do by selecting a tool from up here. I'm going to tell it I want to sketch something. And when I do that, and by the way, we're not doing any 3D sketches, they're all 2D. When you do that, it says select the plane that you want to work on. So when you select sketch, it'll show you the planes that you have as options. You can sketch on a part, but we don't have a part yet. So I'm just going to have you create a rectangle on the top plane. Now we're drawing on the top plane, and it automatically allows you to look directly down at the top plane. That's the origin right there. If you hover over this, you'll notice that. There's the right plane, which you're looking at on edge. There's the top plane, you're looking straight down. There's the front plane, also looking at on edge. So we're looking straight down at this. So if you look at the tools, and I'm not going to go over all of these because you can just look at them and figure out, I'm sketching a shape, which means I can use lines, which is basically freehand with straight lines. There's also splines, there's also arcs, there's also circles, there's also squares, straight slots, there's also polygons, and then you can put fillets between lines. You can put text if you want, which we won't be doing. You can put a point if you want. But I'm going to use a rectangle, but not just a corner rectangle, because every one of these tools, if you'll notice, has an arrow beside it. If you open that arrow, it gives you choices for what type of rectangle you want to draw. I'm going to draw a cube, and so I want it to be centered on the origin. Very important that you use that origin when you create your sketch. I'm going to pick center rectangle, left click, drag out, and make a shape. Now I'm not going to worry about making it a particular length now. So if you're an AutoCAD user, you're probably thinking, oh, I have to tell it what size to make it. What we can do instead is once you place it, and you have that option over here, but don't use it, because what we want to do is have a parametric dimension. That we go up here to Smart Dimension for. When you select that, it allows you, in this case I pick a line, because when we made a rectangle it automatically made it horizontal. it automatically snapped the intersection of those two diagonals to the origin. Those lines are automatically vertical, so you automatically have something that is always a rectangle. So if I pick that edge and bring it up like this, we're in inches. Oop, I never changed. I did change it, but then I started over. So I'm going to go back and pick inches. Now I'm going to right click over here and I'm going to edit the sketch. So now I'm going to double click on this. And you notice the number that it gave me is much smaller because it's measuring in inches now. I'm going to make that 10 inches. I'm going to pick this edge right here, smart dimension, do the same thing, bring that over, make that 10. So what I have now is a square. So that square is something I'm going to use to make an extrusion. Now I'm just going to make, hang on just a minute, going back to editing the sketch. I'm just going to make this, by the way, you are likely to have, when you start this, something that looks like this pop up. I don't know no serious user of SolidWorks uses this. This is really kind of to make beginners have an opportunity to see where they're looking from. It's called a view cube. I find it just gets in the way. Never once have I used it, so I always turn it off. To turn it off, if you go up here to these buttons, little arrow right here, come down and move your mouse over like that, view selector, just turn it off. Spacebar now will allow you to look at it from various points of view, including isometric. So there's no particular reason to have that view cube, and it really does get in the way and slow you down. However, it did demonstrate that right now we are in the middle of the cube we want to create. So I'm just going to go and look at this kind of isometrically like that. What I want to do is extrude that shape. So I need to come back over here and say, well, I'm done sketching. I need to go from the sketch tool to the feature tools. The feature tools are the ones that create the actual 3D geometry. I have an extruded boss, revolve and swept, we'll see those later. I do an extruded boss and I can decide I want that to be whatever length I want. I'm going to make it 10. However, now the origin is no longer centered on that cube. It all goes in one direction. So instead of blind, I'm going to pick that and go down to midplane, and you'll notice now the origin is embedded at the midplane of this cube. I do that, click the green to say yes I mean it, and now I have a cube. So I want you to do that. Then you can pause this video and come back and do some other things. And the other things I'm going to have you do involve cutting away parts of this and putting some features on it. Once you do make this cube, what I want you to do now is to double click on it, find the 10 over here, double click on that and change that to 8, double click on this one, change that to 8, double click on this one, change that to 8. Now it appears that nothing happened, but if you go up here to that little right there, just under that arrow, that's the virtual desktop controls, pick rebuild, and you'll notice it now gets smaller. The other thing we could have done is right clicked on boss extrude and picked edit sketch. Would have opened that up again for us, and we could have edited that sketch. I'm going to discard the changes. And the other way to edit a sketch is to have both the feature and the sketch open, right click on sketch and then pick edit sketch right here. Right clicking is normally going to give you a menu of some kind, and if you want to edit something that exists, right clicking usually has the edit button in the upper left hand corner. So the point I'm making here is you can change the size of this by changing one of the numbers. The reason I did that by clicking on the part itself is because by doing that, all three of those dimensions are available. In the sketch, it's only the two I use for the square. It's not the length. So I can come in here and make that 10. And there are ways, by the way, to make these all connected, but I don't want to get too complicated right now. Make that 10 to go back. Make that 10 to go back. Pick OK. Now the one thing about doing it this way is you then have to tell it to rebuild. And once you've told it to rebuild, it comes out and it rebuilds, and it is now 10. Sometimes it automatically rebuilds, not usually though. So anyway, pause this video, make that happen, and when you're all done, and the person who's monitoring this goes around and sees that, then you're going to come back to this. I'm just going to stop for a bit and leave this up on the screen. And now I'm going to start in again. So what I want to do now is I want to put some holes through here. So I need to sketch first. I need to put some kind of shape on here. And instead of sketching on one of the 3 planes that comes in automatically, once you have something, you're better off sketching on the surface of that if you can. So what I'm going to do, it says it hasn't been saved in 20 minutes. I don't really care. I'm going to throw this away anyway. So you can save it if you want though. So I'm not going to go over here to features, but instead of to sketch. But instead of selecting one of the primary planes, I'm going to go to the sketch tool and I'll just pick one of these surfaces. And it tells me over here what to do. Pick a plane, a planar face, or an edge, or an existing sketch. Well, we're not trying to go through and do anything with an existing sketch, so we're going to pick a planar face, which is right there. Now, and again, it automatically orients itself. You can turn that off, which I do, by the way. Now you put a circle on here, make it look like that, and that circle is snapped directly to the origin because I want it to be centered, and that little glyph is a relation, and it means that it is coincident, that the center of the circle is coincident with that origin. Now again, there's something over here that would allow me to make that a certain size. I could put a 4 in here. I could put a, let's put a 3 in here. That's the radius now. Now, the problem with that is it doesn't actually dimension it. It simply makes it that size. You can see I can just grab that and change the size. So what I notice looking at it is that the line is blue. If it's blue, that means it's underdefined. Now, if you look at the bottom, it says underdefined right there. That means that we need to add something to the sketch to make it unambiguous. So I'm going to put a dimension on here, and the dimension I put on there will drive the size of that circle. So if I take a look at this and say, and it gives me the diameter here as opposed to the radius, let's just make that 6. Now you notice it's black. Down here it says fully defined. Now I'm going to move it around so you can see what's going on with it. And what I'm going to do over here under features is not an extruded boss, which would just put mass inside mass and wouldn't do anything. I'm going to do an extruded cut. In other words, I'm going to take that shape and pass it through this part and cut it. Now, I'm not going to make this 10. 10 would go through this cube right now, but one of the things I want to do is to make sure I make these models in such a way that I can make modifications later on without having to be surprised. So if I were to say make this 10 inches and it goes all the way through, that would be fine unless I decided later on to modify, which of course you do all the time with design software, and make that 11. Now I come back and it turns out that I didn't go all the way through because that hole only goes down through 10 inches. Now, had I, instead of cutting 10, if I instead, I'm editing this now, it said don't go blind, just go up to another surface. Now I can turn this over like that with the middle wheel, pick that bottom and say whatever that bottom does, go up to that surface. So now it's always going to start here and it's always going to end here, so that hole will always go through here no matter what. Now I'm going to go back and I'm going to make my boss extrude 10 again. Instead of 11, gets shorter, and it's still going to go from one surface to the other. Once you've done that, I want you to do this on every other surface as well. So I'm going to do that on this one, but I'm going to leave it to you to figure out how to do it. So this should be paused right now. Go ahead and put a hole through here that's 6, and then put a hole from each of the other directions. And then, when you're all done, if you have had problems doing that, then come back and look at what I'm about to do. What I'm about to do is this. I'm going to put a sketch on this surface now. I'll go and draw a circle. Again, by default it does this. The origin is at the center of the cube if you did this the way I showed you. that little glyph now is yellow, meaning if I left click, it'll actually attach the center to the origin. Left click, drag it out. And again, I don't care how far I drag it out because I'm about to go and put a dimension on it. And the dimension I put on it is going to be 6. If you look at the bottom of my screen, underdefined turns to fully defined once you place a dimension on here. Now, I'll go back to Features, Extruded Boss, and now I'm going to move this around because I want it to come down to here. So I'll say, yeah, go up to Surface, and then pick that surface. Now it's always going to start at the top or start at the side and then go through to the other side. Do the same thing here. So let's put a sketch on that surface. I'm going to put another circle, and again it's going to turn. Now you can turn that feature off. I'm not turning it off because I know that's what it's going to look like for you, and I'm not going to get into customizing on this yet because you don't know yet much of what you're doing. Although the one thing I would customize is get rid of that view cube. It's just awful. Funny, new users tend to leave it on because it came that way, but really I'm just telling you it's in your way, so get rid of it. Smart dimension, grab this, bring it out, make that 6, black and fully defined. We go back to Features, Extruded Cut. We need to move it around so we can see it, so we have to do that. Now up to Surface, pick the surface that goes here. So now you can see what you've got is 3 holes that go through this. Again, you can pause right here to finish that up if you need to do something. Now what I'm going to do is I'm going to add some features without having to do a sketch first. And there are some features you can do that with. Chamfers and fillets are one of them. Now, right now, I have done all this work, and I'm thinking, boy, wouldn't it have been easier for me, and it would have, to put I'm going to put chamfers on each of these edges. You'll see what those are in a bit. But it's possible to pick a surface and say chamfer all of its edges, but right now I've got edges I don't want chamfered as well as edges I do. So I can do a chamfer by going to the fillet tool under Features. There's a little arrow, and picking chamfer instead of fillet. Then I can pick every single edge. But that's going to take me a while to do. I can do it, but it's something I don't want to do. So I'm going to come back over here, and this is another really powerful element of 3D modeling with parametric modeling. If I move my cursor so it sits right on that edge, when the little fingers come out like that, left click and hold it and then drag it up, I can go ahead of what I've already done, and then while I'm up here I can insert another feature. So I'm going to go and say I want to chamfer that surface, that surface, that surface, move it around, grab that one, grab this one, move it around, grab that one. Now that gets all the corners I want without getting the circles, and I don't have to pick them individually. And then over here I can say let's just make that a 1/2 inch. Come back out like this. Now every one of those corners is chamfered, which is a surface that is flat that connects two other surfaces. Now if I roll this back, I get my openings right here. Now I'm going to put a radius, which is a fillet, on each of these openings. For this one, I can't pick the edges because it'll put a fillet on all these edges. But by rolling it back, it made it a lot more efficient for me to put the chamfers in. A fillet is a radius that's tangent to two other surfaces. So I'm going to pick a fillet for this, and it's tangent to that surface and this surface. Let's make that 0.4. Now once I've done that, I'm not going to stop. Instead, I'm going to keep picking edges because I want all of these fillets to be the same size. Now there are 6 of them because there are 6 surfaces that it went through. Don't pick the inside edges. Pick the ones on the outside like that and like that. That should be all of them. It is. So now when I pick the green check, they're all the same size. Now these edges, these lines right here, show the tangency, and that's just because computers recognize that surface is different from this one, so it puts an edge. If you were to come up here and say don't show the edges, it would look like that. So you have edges right here, sharp edges, because that's a flat surface. Here those tangencies don't show up because you wouldn't actually see them. Some people like working like this, I like the view to look like this, just because it's easier to see what I'm doing. Now, once you've done both of those things, and again, you want to pause this video at each of these elements. And I probably should have said pause before putting your chamfer in, and then pause before putting your radius in. And then go back and take a look at this. And you can also rewind this as well. So now, let's find out if yours is the same as mine. I use 10 for the dimension of the cube. I use 6 for the dimension of the holes. I use 0.4 for the fillets and 0.5 for the chamfers. Now what I'm going to do is add a material to this. I'm going to say, let's just make this out of something. Right now it has no material specified. I'm going to right click, and I'm going to come down, and there's a partial list of the materials available. So let's just find out what this thing would look like and weigh if it were made out of plain carbon steel. Now it doesn't change the looks very much, but it does make it a little grayish. But what it does is assigns a material based on the density of plain carbon steel and a number of other characteristics as well, which means now I can use a third tab up here. And we're going to use Features, Sketch, Forget Markup, and then Evaluate. Under Evaluate, I can go over and say, what are the mass properties of this? And the mass properties of this are that that cube would weigh 123 pounds. In other words, if this were made out of plain carbon steel, 10 inches by 10 inches, it would be hard for most people to pick up, 123.68 pounds, and it also gives me the volume. If I were to say, what would it be before I do any of that stuff to it, and I come back up here and I say, what are the mass properties? Well, now the mass properties of that solid 10-inch cube, 281.79 pounds. Change the material. Let's just go and find a different material here. These are all metal. Well, let's go to copper. We'd make it a copper material. We come back up here to markup. We go to mass properties. And you notice now copper weighs more than plain carbon steel. 321 pounds now. So this is a pretty heavy block of metal on here if you make it out of solid copper. But you have other choices for materials as well, and they're very accurate, by the way, and I know because I made a part one time, complex part that I got from a company. I modeled it in SolidWorks, checked the mass, and when I weighed it on a very accurate scale, it was within a couple of grams of being correct. So that's, right click. Okay, so edit material brings up all the various materials that you can select. So right now we've got steel, iron, aluminum alloys, copper alloys, all kinds of things going on here, but you also have plastics, woods. So if I were to decide I want that to be made out of wood, let's say mahogany, which is a relatively heavy wood, now it shows me kind of what it would look like. I go back over here now to features, to evaluate, mass properties, and now we're talking 21 pounds if that's made out of wood, which makes a lot of sense. I'm just going to undo all the stuff I just did by going back to materials, right click, go back to plain carbon steel, bring this back down now, and what you can do is just go and check the mass of what you have and see, did you get 123.68 pounds? If you didn't, that's okay. It just means you didn't do exactly what I did. So that's one way of checking things. So now I'm going to eliminate this, and I'm going to show you some other things as well. So now we're done with this one. Do I want to change anything? No, I don't think so. Okay, so we're done with this one, so I'm going to go make a new part. I'm going to make a new part. Again, if when you opened up SolidWorks for the first time, you identified millimeters as your standard, you're going to have to change this. Now, you can also change the default as well. So what I'm going to do right now is have you do something with a different method for creating a shape. So if you look under Features, you've got Extruded Boss, you've got a Revolved Boss up here as well. So what I want you to do is to go back to the Sketch tool. Everything starts with a sketch. Then I want you to create a sketch by picking the tool called Sketch. Again, the tab simply allows you to get access to those tools. It doesn't do anything. This asks you for a surface or a plane. I'm going to pick this plane right here. Now I'm going to use a line, and I'm going to use a different kind of line than a standard continuous line, I'm going to pick a center line. I'm going to move my cursor down until it lines up with the origin. And when I see that blue dotted line, left click, I'm going to drag this line through the origin until I get the yellow coincident and horizontal glyph. And now I have this construction line. It's called a center line in SolidWorks, but it's essentially a construction line. Sometimes they call it that. And what I'm going to do is just create some kind of crazy shape up here. And you'll see in a bit what I'm after here. So this shape right here is going to have some straight lines. It's going to have some curves. I'm going to just do something nutty. And I'm not going to try to fully define it. I'm just going to make it a closed shape. As long as it's a closed shape, this is going to work. And up here, we've got shaded sketch contours. That's on by default. But if it's off, you don't know that you closed that properly. So having that on is really helpful. So you notice it automatically added a perpendicular relationship between those two lines, tangent relationships between the straight lines and the arcs, and I did that with a little special technique. But those are tangencies. Vertical for one of those lines because it was close to vertical. This was also close to perpendicular. Now I didn't tell it to do that. I just got close enough to those so it did it on its own. Now I'm going to go back over here to features now, and I'm going to do a revolved boss or base. And when I do, it's going to look like that. In other words, it's going to take that shape and it's going to extrude it by revolving it around a center axis. So now I have a shape, very complex shape, that I use the revolve tool to make, and I can use that for any number of shapes as long as what I create is the cross section. That was what I show up here, the cross section of the part that I want to revolve. I go back to our PowerPoint. You'll see this is actually an actual part. It's a wheel, and that's the cross section of that part of the wheel. There's a center line, which is the axis that goes right down through the center of that wheel, and I sketched this shape above the center line so that it would leave a big hole, which is what I did in the other one as well. In this case, that's a fully defined sketch because it's an actual part. I'm not going to waste time right now having you fully define everything. I just want you to understand that if you were making a real part, you would. If I go back now to this, that is the same process as making that wheel. So I want you to do something with that as well. And what you have to make sure you do is this. When you get done with your sketch, just make sure that that sketch is shaded when you look at it. In this case, you can see a little bit of shading. Make sure it's shaded when you look at it. In fact, let me just get rid of the revolve. I'm going to right-click on the revolve, and I'm going to delete it. That's going to leave me with just the sketch. I'm going to right-click on the sketch. You notice there's a negative because it's not fully defined. You don't have to fully define it. So it's got to be shaded. If it's not shaded because something like this happens, then you go back over here to features and say I want to revolve it, and you pick that for the line. It's just going to go, nope, you can't do that. You can't do it because it would not work in real life. It's open or self-intersecting or intersects the center line. So it doesn't intersect the center line, but it's self-intersecting. Pull that down. Now, if it looks like that, it's going to work. Looks like that, it isn't. Looks like that, it's also not going to work because it goes across the center line that I'm trying to use. So if I went over here to features and I said let's do a revolve, and I pick that as my line and I do this, I'm going to get the same message. So those are the two things you have to worry about. So right now, that would work. And no matter how crazy this is, as long as it's a closed shape and it's not self-intersecting and it doesn't go across the center line, as long as those things are true, you got to be a little careful on this one. As long as those things are true, you'll be able to do a revolve, but it won't do anything that's geometrically impossible. So you can see that's a pretty complex shape right there. Bring it out like that. Looks like this. Just barely misses down here. Now I've got that cut in half just to be able to look at it. It looks like something like that. So pause the video again and go and fiddle around with that and see how that works for you. Now I assume that you have unpaused the video. So now we're going to take a look at another mechanism. So if I go back to this and I go down and look at this sheet, this is a sweep. A sweep is when you have a path and you have a shape. In this case, I was making a cotter pin. And cotter pin, if anyone's ever used one, you probably have all seen one. You put it through a hole of some kind, then you bend the end so it can't come out of the hole, and it's used to hold something in place. It's literally half a cylinder. The wire itself that's used to make it is drawn out as a wire and then sliced in half, or it might be drawn into out through a die as an extrusion. It looks just like that letter D. Looks like a letter D backwards here. And now that is the cross-sectional shape of what that looks like right there. So what we're going to do is a sweep on this one. But I'm not going to have you, well, maybe I will. I might have you do a special shape. So now, as a swept solid, looks like this. We'll start a new file. Again, it doesn't really matter what units you're using here because I'm not actually creating anything where I'm going to give it units. But you do have to make sure that you are using the units you want. Otherwise, it creates a real problem for you. I'm going to go back to inches. I'm going to start by doing a sketch on the top plane. And I'm going to do a sketch using a spline. And I'll just start splining like that. A spline is a series of tangent curves that are defined to be tangent curves. And when I come here, you'll notice it sort of changes so that everything's tangent. You can control it with various tools here. You can do other things you want as well. It's fairly hard to fully define a spline. You have to really put a lot of dimensions on it in order to do it. But that's what I want for right now. And now what I'm going to do is that, and I don't have any features on this yet because I simply want a splined shape. It doesn't have to be closed either, by the way. In fact, let's not close it just to make that point. It can be closed, but it doesn't have to be closed. So we'll do it again. So let's just have a path, and let's just say we have a piece of hose or a wire or something. We want it to go along this path. So we're going to have it look like that. Now, pick OK. So now that's what's called the path. Now in order to put a shape on here, we have two choices. We can go directly into the swept boss or base, and we can, instead of picking a profile that we want to sweep along that path, we can say just make a circle out of it. If we do that, we have a chance to put the size of the circle in here, whatever we want, as long as it doesn't get so big that it's impossible. Now we can make that big enough and it's going to intersect itself and then it won't do it. So we didn't make that big enough yet. But you know, at this point, when it goes through, it probably will. So you see what it's doing there. Well, it might still be possible now that I look at it. Let me go ahead and make that 6 inches. And you notice it just won't do it. And it won't do it because it is impossible. It would intersect itself. Do that, it'll come out like this. So that's how you can just put a circular path on here. But we can also put a sketch of some kind. So if I were to take and make another sketch, and here's what I'm going to do. I need to sketch something on the end of this, but it has to be 90 degrees to the end of that. So what I'm going to do is create something called reference geometry. I'm going to say, let's make a plane that's based on that spline and goes right through the end of it like that. So you notice what it did. It put a plane that's 90 degrees to the end of that, and it's 90 degrees to a straight line drawn tangent to that spline at that point. Well, what that means now is I can go ahead and put in some shapes. So I could put in, for instance, I could sketch on here, and I could put on a circle. Just snap right here, put a circle in here. And then if I wanted, I could put a polygon. Put the polygon in the same basic location, have that looks like this. So now what I've got, and you know, I can fully define this, and I almost always would. So let's just say we want that to be a 1/2 inch. Let's say we want the polygon distance across flat to be 2 inches. And then let's say we want that edge right there to be vertical. So now we should have, no it's not for some reason. Yeah, we want those two things right there to be coincident. So let's do that. There we go. Now we know that the location of that, we know what it looks like. Might be that we want to change this to 1 inch. There we go. All right, now we have two separate sketches here. One of the sketches is a profile and one of the sketches is a path. So now if we go back to features, and you notice I'm not in a sketch right now, and then under features I say I want to do a swept boss or base. Now this is the profile. This is the path. When I pick that, it goes through and looks like this. So now I've got a shape that looks like that. It's this hexagonal shape, and it's got a hole that goes all the way through it. So what I want you to do now is to do something that will require a swept boss. And you can make it circular, or you can do what I did by putting a new plane in there. And I guess just a reminder of what that would look like. I'm going to get rid of this sweep. And I'm going to get rid of that sketch. And I'm going to get rid of that plane. Just deleting it now. So the way I put that plane on there was I went under features to reference geometry. I picked the arrow and said I want to make a plane. I said I want the plane to be defined by that spline, and I want it to go 90 degrees to the end right there. So it gave me a new plane that I could draw on, and once it did that, now I can sketch on that plane the way I sketch on any other plane. So I go to sketch, sketch. Now it turned around. I can come back and do this, and there are ways to flip that, but again, I don't want to get involved with that right now. So now I'm going to go back over here and do a sketch, and we'll do an elliptical sketch. So we do our sketch here. That looks like this. Come back out. Now you have two sketches. One's 90 degrees to the path. The other one is the profile. Now when we go over here and say I want to do under features a swept boss or base, the profile is going to be this, and the path is going to be that. Now I have an elliptical solid that goes through a sweep. So now pause this video and go and try one of those. The next process for creating a solid model I want to talk about is a loft. And this is the one most directly related to hull design. So here's a case where we have one of those body plans, and I have both the stern and the bow, and I use them to create a series of shapes. And those shapes are separated by what I referred to at the beginning as stations or ordinates. And then the software creates a shape that goes from one to the other more or less fluidly. Now there are all kinds of things that I could do to make that work better, but for the purpose of this workshop, we're going to just go ahead and do a loft based on something that I've already created. So it starts out looking like this as a series of sketches in SolidWorks, and it ends up looking like this. So let's go back to SolidWorks. In this case, I'm not going to start a new file. You're going to open an existing file. So what I'm going to do is to open up a file, and that file will be on the R drive, and it will be under the BIW folder. And if you take a look at where it says SolidWorks, Loft Exercise, I've got two. One of them is complete, and one of them is the exercise itself. So don't open the one that's complete. Open the one that's the exercise. When you open it, it'll look like this. Well, looking like this means that I've gone already and I've created a series of planes, and you can see they're called plane 1, plane 2, plane 3, plane 4. If I were to look at this from the front, you can see that they're all separated by the same amount, and they represent the equivalent of a shear plan. Let's go back and take a look at that. The equivalent of a shear plan right there, right there. The equivalent of a shear plane. Each one of those lines right there, which are ordinates or stations when they're building it, is where I have an individual plane. So that individual plane has the shapes coming through like that are based on, you can see what I did is I brought in that sketch that I had, or that drawing that I had, of a body plan with both the stern and the bow. And then I just traced over those shapes, which is not going to be a very fair, in other words, it's not going to be a very smooth transition from one to the other. But what I am going to do is, when I separated them, is have you go through and create a loft on them. Now, creating a loft means you start with all those sketches, and you notice none of them are fully defined because I just traced them. So there are 10 planes, 10 sketches. I'm going to go up to Features, Lofted Boss or Base, and what I want to do is pick each sketch and try to pick them kind of close to the same location in each case. So for instance, if I do that, it makes a loft that looks like this, one that looks like that, one that looks like this, and I'm picking the bottom just because it's easier to pick it in the same location. If I were to pick a point like this, it would end up twisting in order to locate that point correctly. But you can then pull down here, for instance, and get it to look more like that. Now, I'll take that one, and I'll take this one, and this one. Now, I didn't have that come to a sharp point. I would have added that later, although there is a way to do that. So when I'm done, looks like this. Now, all the planes I've got showing, but the sketches have been subsumed. If I say let's just hide all those planes as well, that's what it has. Now, obviously what I'd have to do now is go and get rid of that top surface and that bottom surface. And that is, whoops, something happened over here. Yeah, something went wrong here when I was bringing it across, so I think I just selected possibly in the wrong location. Let me see if I can edit the loft and see if, I don't know why that, well, you can see I did not improve it when I was trying to make that change right there. You open up the one that I already did and see if it looks like that there as well. Yeah, well, this model is a little more, yeah, and you can see, no, I even finished this one by putting the bow on. And you can also see that, so let me just turn all that stuff off too. You can see that I put a deck on it. I pulled the top off, put a deck on it, gave it a thickness, so you have a hull thickness there, and then put that little point on there as well. So the way I did that was, I got the loft done, looked like that. Then I shelled it. By shelling it, I was able to remove the top, so it looks like this. And I gave it a thickness, and then I just said get rid of the stuff at the top. Then I probably put the nose on there as well. You can see that did not cause that problem when I did it before. So when you're doing yours, experiment a little with where you pick it and see how it comes out. Then, not sure what that was for. That was, oh, a couple pieces on the side. Not sure why I put those on there. I might have just been fiddling around with something. And then body move, copy, combine. Got it. So I was adding a little piece there, and I used a function called combine. So it wasn't meant to stick out like that. It was just temporary. And then if I were to come up and get rid of the tangent edges, looks like that. So that's not too bad. It's not really all that fair, and there are all kinds of tools you can use to make that happen. But that's where I went with this part after making the loft. So I want you to go ahead and do a loft on that as well. Then you can pause right now, whoever's running this, or if you're watching it yourself. Now I presume that you've unpaused, so let's go back here. So we are all the way down through here now, where you did the loft. And so what I want to show you is a couple other things. A shell, I just showed you something about a shell. But let me just quickly show you how to do that. You can try one or not as you wish. So I'm going to do a new file. I'll do a part. I'll go and, again, it doesn't really matter for what I'm doing since I'm not putting dimensions on. So we'll do a sketch, and I will do that on the front plane. I'll have a center line that comes down through, looks like this. So let's just do a little bit of a goblet, kind of similar to what I had there. I'm going to come out, come up, come over here like this, come up again, maybe come out and do a little something like that, come up again, come out to here, come up to here, and then go back to there. Alright, now what I'm going to do, and then I have to close it. So I'm going to close it by going from here to here, and when it's closed it should be shaded in. It is. So now we'll do another, but I'm going to do another one of those revolves. Looks like that. Didn't take very good care. Looks a lot clunky. But just to show you how the shell function works, if I go up and pick shell, I can find right there under features, and then select any surface that I don't want included, and then give it a dimension for the thickness of the shell. 10 millimeters would be too thick, I'm thinking. So let's go with 2 millimeters, and then pick the green check. Looks like that. So what it does is it shells it if it can, and this one could go all the way down through. Shells it if it can, and then it leaves it open. So that's the example of a shell. And then, okay, solid modeling with SolidWorks, combined shell, sweep, extrude, cut. So what I'm going to do here is I'm going to show you an actual project. This was a mask that I made for a company in Lewiston. This is at the beginning of COVID. They could make fabric that was N95 compliant, but they didn't have a technique for making a full mask. And at the time, N95 masks were very hard to come by, especially and most importantly for medical people. So they thought if we could make the material and then have that material be developed and manufactured in packets, that could be then put into an existing silicone mask that the medical provider would then put on their face, and they just replace the little insert when they needed to, and then clean the mask itself up. So I said, all right, I'll take that on, and this was quite a project. So what I'm going to do is go through and show you how that one progressed, and then I'm going to show you a full project, which is the ballot boxes that the state of Maine uses for voting, which I also designed also during COVID, because people were reluctant to go to the polls during COVID. Yeah, so let's do that. So I'm going to open up a couple of projects, show you, and these are projects that I created, and I'm going to walk down through and just show you how they were created. So this is the mask and the holder for the insert. In other words, fabric would go in between those two surfaces right there, and then you would put the whole thing into the mask, and it had a place for a receiver. Whole works. Now I actually printed these with a material that was flexible with a special printer that I have. And printers known as it's a resin-based printer, known as a Formlabs printer. So when I printed this out with the material that was very much like silicone, it actually sealed extremely well, and it would have worked really well. However, the mask shortage went away before this company was able to get involved, and so they had prototype. They had gone to an engineer to have the thing prototyped in order to have it injection molded in silicone, but then when the mask materials that were being generated and manufactured, the typical ones, the ones you throw away, when they became more available, we pulled the plug on this. So what I'm going to do though is show you this. I'm going to open up the part itself, the mask itself. I'm going to back up. Yeah, it's an older version because we've updated. So I'm going to go down and I'm going to grab the bottom and do something I showed you earlier, which is to bring this all the way up here till I get to this point right there. That point right there is a loft, and that loft contains a number of things. That shape right there, that shape right there, what's known as a guide curve right there, and another guide curve down here. So the way I did this was I took photographs. Actually, I had a number of people take photographs of their faces from the front, the side, and I took one of myself, the front, the side, and the top, because I wanted to have 3 views of this so that I could get a sense of what that shape would have to be in order to fit on somebody and fit over their nose and under their chin. So I just traced that shape out and traced this as an elliptical shape, and that's because I was going to put that, the packet in there. And then this guide curve, which is like something I could have used on that ship, or that, that loft you just did, it just tells it what direction to take as it goes through, and it tends to smooth things out. So here, it kind of brings the nose part down like that. So I just did a loft between this shape and this shape. And then I use the guide curves to tell it how to form that loft. Now once I did that, I have another shape, and that's from the side. And I just extruded that through, and I just made it go all the way through the part. So now they're overlapping each other. Now the reason I did that is because what I want is a mask shape that is the common mass of those two shapes. This is the shape from the side. If I take a look at it like this, you can see what that shape is doing. And I wanted it to come up with a shape that was the overlapping part of those two. Now that's called a combine in SolidWorks. And when I did it, I got this shape right here. So you can see that it comes back where it's going to go over my face more appropriately. Now, that's not a mask, obviously, so the next thing I did was shelled it. And shelling just meant getting rid of those two surfaces right there, and then giving it a thickness. Then I did a boss extrude. And the boss extrude in this particular case, what did it do? Oh, yeah. Boss extrude in this particular case gave me a projection that was then shaped consistently so that I could then put something in it and have it held in place there. Sweep in this case was probably, I don't remember what it was. Oh, I don't remember what it was, and I suppressed it. Okay, I see why I suppressed it, because it broke something. So here's what happens if you do something and it breaks. And this, by the way, happens a lot when you're designing something for the first time. It says, no, that sketch you just created and that shape you created, that's going to interfere with something, so get rid of it. So I did. I just said, let's take it. I'm going to right click and let's suppress it. That means it is still available to me, but it's not going to work, so I suppressed it so it was gone. In fact, wouldn't be a bad idea for me to just probably get rid of it. Must be a reason why I hung on to it. I have a 3D sketch. Oh yeah. Alright, well, it's not part of this right now. And I've kind of forgotten some of the things I did. So then I did a fillet, and that fillet simply made a smooth transition from the mask to the part that extruded. Came over here to the boss extrude, and I put in a little shelf so that it would hold the part in place. And I did another fillet right at the outside edge of this, the bigger one. Cut sweep. I did that along here, and that's to have it taper down at the edges so that it would fit on a face better. Then the rest of it is just putting the ties in. So I needed planes to do that. So what I started doing then, I made a new plane to put that on. And then a sketch. Let me see what happens next. So planes. Okay, I see. So now what I was after was getting that tie in right here. So what I did after I got that tie was I filleted it so it was smooth all the way around. Then I mirrored it to go to the other side. And it did. So I had one on the top and one on the bottom. Went to the other side. Cut extrude. Oh, so when you put the thing in, I put a little tab on there so they could straighten it up to go in there, because it's an oval shape, so it can't go in any position. And then that's it. So that's how the mask itself is made. Now the other thing I wanted to show you, again, I'm just showing this to you. I'm not expecting you to do that. But the other thing I wanted to show you is this. Now this is a full-blown project. The governor of the state of Maine contacted the president of the community college system, and since I'd gotten some publicity on something I did for Maine Medical for the COVID thing, there's a ventilator component, and then the mask thing, she called and asked if it'd be possible for me to be assigned or to be asked to do a design for ballot boxes, because they wanted to use drop boxes so people wouldn't have to go to a polling place for the election that happened immediately after COVID hit. But none of the companies that make ballot boxes had any in stock, because every state in the country was trying to do the same thing. So we had a number of things, and they were called design criteria. One is it had to be something we could manufacture in a hurry, so it couldn't be one of the fancy kind of mailbox ones that has a weight on it and opens up and then goes back. Really had to be made out of sheet metal. It had to be simple and yet secure. Had to keep water out. It had to be something that could be locked, both the part that takes out the ballots and the part that the ballots go into. And it had to be rugged. It had to be something that couldn't be tampered with very easily. So that's a little more involved than you might think. It looks like just a box with a slot in it, but for one thing, it has to have a cover for rain, and that slot has to be back there so that if the rain is being driven by wind, it can't then fill up the box with water. And the wind-driven rain of a 100-year storm would come at an angle that is just shy of enough to get in there. So that's what I was doing as far as the design goes. So I'm going to open this up and show you the drawings themselves, show you some of the components, show you how the sheet metal part worked, and then just show you what the whole thing looks like as an assembly, as an indication of what an entire design project would look like start to finish. So now this is the first sheet in one of 7 in the drawings that I provided to the manufacturer who had bid on this and got the bid and was going to make them for us, and did in fact make them. They made 76 of these so fast. Humphrey's Barbecue down in, I've forgotten the name of the town now, but in the southwest part of the state. They just pulled everybody in and they welded up these things in stainless steel, and they just worked like crazy, and they put them on a truck, and 2 weeks before the election took place, they had them all in place, and they were used by 76 different communities in Maine. And I was told recently that 70% of the people who voted used the ballot box. So, and it might be 70% of the people who voted absentee used the ballot box. I'm not sure, but a lot of people use the ballot boxes. So right now, what I have here is just what's called an assembly drawing. It just shows what it looks like all put together. And I made 2 sizes, and they did manufacture 2 sizes, and these are the larger ones. This is the one used in Portland, and they first put it up. Within 2 hours, it filled up, and they had to start emptying it multiple times a day. So the big one is what they needed. In some towns like Rumford, which is my hometown, they used one of the smaller ones. So I have a couple details in here just to show how I wanted that to be done. That door in particular was critical. I didn't want to use a gasket because it wears out. Makes it a little hard to close sometimes. So we had a piano hinge across here. I wanted to make it clear that that had to be welded. And then it's got flanges that come up on the sides so that water can't get in from the sides. The other sheets are individual parts. So here's the cover, the door at the bottom for opening it up. And here it is folded, and here it is unfolded. It's known as a pattern drawing in sheet metal. Gave them all the dimensions that they needed, but I gave them step files of each part as a pattern, and they use those step files to drive their laser cutter. And the laser cutter just cut all these parts out. And the only thing they had to make a change in is I had one part was really too big for them to fold up. So they had to modify that by having one more cut than I had called out. So you see that's the door cover. Come over here, that's that hood that goes in the top. That's the pattern that has to get folded up. And there was a slot there to put a door into. And that door that slid in, that's not it. That's actually the large box itself. So you can see where the flanges come out here. You see there's another flange down here. Come over here. And that is the flat pattern of the large box with all the folds that have to be made. And what they had to do here is cut it here in order for it to fit on the equipment that they had. And we come out here. That's the door that goes in the hood and the top and slides in. And I designed that so it could just stay in there. It could be locked open or locked closed easily. Didn't have a hinge on it to try to simplify things. And then that's one of the small boxes. Everything else is identical, so the small box is just narrower. Now if I go back to sheet 1, that's the set of drawings. If I open up the assembly looks like this. Assembly looks like that. And it's really nice that I had it because it made it a lot easier for the people in the Secretary of State's office to understand what I was pointing out to them. So you notice this one right here is locked. Well, that's a little door that comes down and it locks in the hood. Now locked down here. So that's been at the end of the day. They would go at the end of the election day. At 8 o'clock they locked this. They opened this. I took everything out. Then they closed it and locked it up again. And that meant that was it. That was the end of voting. I made 2 different versions of this. This one, that's for voting. So you open it up, you reach up in there, you do your ballot. That's locked so then nobody walks away with the door. But the door just slides into that slot. Worked really well. Although most municipalities just took the door inside. I would have padlocked it so it didn't get separated. But then you lock this up like that while people are voting so no one can reach in and do anything, nefarious. Well, if we open up any of these, let's just open up the big box. If we open that up as a part, this is the original part of that. And what I want to do is just show you briefly how this was generated in SolidWorks, which is why I was able to do it. I worked in a sheet metal shop at 15. My uncle was the owner of the shop out in Detroit, Michigan. It was illegal. I should have been 18 to work there, but hey, nobody questioned it. I was a big kid, grew up on a farm, I could do work. And I loved the job, it was great. But I was always amazed that my uncle could figure out the flat pattern for something based on how it was supposed to look, because he couldn't start with this shape. Instead, and I'll show you what I mean here, that's the flat pattern. So what he would have to do is make a pattern, mark it up. My job, and the other people in the shop as well, would be either to cut or to fold at these fold lines, and when it was all done, fold it up. Then we'd have to go back in and we'd have to weld it up. Now you notice that all the corners have this little relief, because you can't just fold it with a square corner. It would bunch up and it wouldn't work very well. And then you have something down here that had to be folded multiple times. And then the tabs here had to be folded, but they also had to be cut. That's why the laser cutter was so nice, because they just fed this file to the laser cutter, went around, and it had this thing all cut up. So what I'm going to do here is to close that up. So here's how the process works with SolidWorks. I started with a shape that I wanted to end up with, and that's just a solid piece. I did an extrusion with that shape right there. Then I said, I want this to be turned into sheet metal. I said, all right, that's great, but in order to do that, next you have to convert it to the type of sheet metal you want. And you notice now it's showing the radius for the bends, and it's also showing that little relief right there. The gap is because it's going to have a gap in order for the welding to take place. And then I said, all right, once that's done, we got to put a slot in it. The actual slot's actually narrower than that and back further, which is what I wanted. And they made it that way. But anyway, cut extrude, that's probably holes. Yeah, there's one hole in the bottom right there. And that might be the drain hole. It might be the hole for bolting it down. No, that was for bolting it down. Then I put the drain holes right here. Now another cut had to be opened up over here. So that was our next cut. Had to put a plane in there to draw on. Some more holes in the back also for mounting. Now the company that made it didn't think that was a good idea. I wanted to be able to mount this from inside that door, so when you locked it, nobody could take the nuts off and walk away with it. They ended up putting angle iron on the outside, and everybody just bolted it to a wall. Nobody walked away with it, however. Now this is known as an edge flange, and you notice there's one little piece that comes up and bends. These are all sheet metal tools. There's another one on the side, that's so the door can come down over it. Another one over here, I just mirrored it across. I had to get rid of that corner right there, or it wouldn't close. The door over it wouldn't close. And that's one of the beauties of using a piece of software like SolidWorks, is you can put it in there as an assembly and then try it and see where things are going to hit and then make a change. Another edge flange down here, so it goes down and then it comes out and then it comes up. No, it just comes out. And then there's a hole here. So what that means is the door comes down over it, slot in the door goes over that, then you put the padlock in so no one can open that door. And then the flat pattern was resulting. So that's how this thing was generated, and all of that went from here to an assembly file. The assembly file looked like this. And again, the assembly file allowed me, when I was doing this, for instance. Oh, no, I don't. When we were doing this, the assembly file allowed me to go in there and say, let's see how this is going to work. And this is when I discovered that if I thought there was going to be a straight corner on that, and I thought I could pull that down across it, it was going to bang into that corner right there. So I had to go in and get some relief on that, and I was able to do that with this. And you can see I could also make sure that the slot was going to line up with that tab that came out. All of these, by the way, are not shown welded. They're just shown as it's folded, so that's why there's still a gap there. And then up here, this I could take in and out No, theoretically is locked, but it's not real world stuff here. But that just slides, comes up like this, and then folds. It just you lay it back down, and when you lay it back down, in fact, in this case, folds that way and then comes back. And once it goes back, those two holes line up, and you can lock it in place. So it looks like that. So that's how that is designed to go. Now let's go back and take a look at the PowerPoint. And that is it, really. We don't have enough time because it's only half a day. I was planning on having to do a part like this from actual dimensions. And that was up here. Now I am going to ask you to try to put something together as an assembly. So I've got a part right here. And in fact, I don't know if you're going to be able to see it in a little bit of video right there or not. But this is what's known as a toggle clamp, and it clamps by pulling or by pushing. And I bought this and then created, actually somebody else might have created that model, can't remember, but it's got a couple of tie rods on it. It's got a piston that comes up through, it's got a lever that locks in place. When it's down it locks, when it's up it locks. So what I'm going to do is show you what that looks like. I'm going to give you some parts, and I'm going to have you put them together by making an assembly, and you probably won't finish it, but you'll get a sense of how assemblies work. Then you will have seen the whole picture when it comes to parametric software. So, oh, and there's a good photograph of it, so I didn't have to show you on camera. That's what this thing actually looks like. That's what it looks like in SolidWorks. So now, and this would be another assembly. If we'd had time, I might have done that. But I overestimated how much I could get done in this period of time, and I've done this multiple times, and I know we're never going to get to that one. So here's what we're going to do. I'm going to have you make as much of this as you can. Now, when you create an assembly in SolidWorks, when I say SolidWorks, I mean any parametric software. You want to start with a part that holds everything together. In this place, that base is the only logical starting point. So that's where I'm going to start when I bring that in. So what I'm going to do, let me open up an assembly and I'll show you what it looks like, and then we'll bring in the individual parts. So this is the toggle clamp put together, and I'm going to show you how it works. So look at it from the side. You notice how that comes down, and it can come all the way down till it hits the base, and it doesn't go any further than that. Now the question is, will that work as a clamp? In other words, it's pushing it forward. It's stopping here. Will that prevent that from pushing back? And if you notice, if you try pushing back on this, nothing happens. Try pulling forward on it, something happens. Then you try to push back, and now it would open up. So in order to work, it has to go all the way down till that tie rod is past the horizontal point. And when it does and comes up against the base, now any force pushing back on this is going to try to drive that through the base, which of course is impossible. So you can use that to clamp in that direction. In other words, push that down and clamp it. You can also, though, because it's got a threaded hole in the bottom, you can also open it up. And as you open it up, you can pull on it. So you can put tension on this as well. In other words, this clamp is bolted down to a table. The thing we're dealing with is also either bolted down or put in between this and a stop. Now, in the opposite direction, this gets to this point right here. It's not going to stay there, because if it got any tension on it, it would just open up like that. But if you go all the way down till it hits the base, now attempting to pull it in that direction, tries to pull it through the base, and again, it can't do that. You push it back to a point. Then, when you pull it, it might go down, it might go up. If it's any amount at all above horizontal, pulling it opens it up like that. So now, here's how you're going to put this together. I'm just going to throw this away. What I'm going to do is open up the parts from the folder that I have called Toggle Clamp. So again, this is what you're looking at. This is what it looks like in SolidWorks. Like that. One of the things you need to notice is that the bend in this comes straight up. The hole at the end is the one that goes through that little tab from the base. The tie rod goes through that hole that's at the elbow. And so it has to go up and then go to the right in order to work. And so that's the way I've got it set up here as well. Up and to the right. The bottom is where the pin goes that pivots around, and that's where the tie rod goes. So if we go back to SolidWorks, and I'm going to start a new assembly file. So don't start with a part, start with an assembly. When it first opens up, it's expecting you to put in the first part. So it's going to open up a dialog box like this. So we're going to go to SolidWorks, toggle clamp, and the only starting part that makes sense is the base. So you pick the base. So I want to open it. Now you can drop this anywhere you want, but that's not a good idea. Instead, on the very first part, go to the green check over here. When you pick that green check, it just puts it in place. Now we have a different set of tools here because it's an assembly. So under the Assembly tab, Insert Components is one of the tools, and it asks you to go and browse for the components. At this point, we don't bring in just one thing. We bring in the tie bar, hold the control key down, the push rod, a pin, and the cam lever. Now we're just going to put these anywhere because they're not going to be constrained, and we'll use them as we need them. That pin, by the way, has two different configurations, short and default. We're going to use both of them at some point. And then we have the tie rod. Now the very first thing I'm going to do is take that piston right there and put it in that hole. So now what we're going to be doing is something similar to relations and sketches, but they're called mates. So we're going to say we want to put a mate between that and that. If you go to the mate tool under assembly, it looks like a paper clip. You go up here, and these are the possible standard mates: coincident and concentric. Those are the only two we're going to use for this. There are also advanced mates. Now we would use the advanced mates or the mechanical mates in order to do certain advanced things, but for right now what we're going to do is just stick with the standard mates for what you're doing. So we'll pick standard, and what we want is a concentric mate. In other words, we want that cylinder and that cylindrical hole to share the same center axis. Pick that, and now when we move that, it will only go in and out of that hole. Okay, it still can turn. We haven't constrained that. Now we're still in the mate tool. So now what I want to do is to take this lever and put it on here. So we're going to move it by left clicking and holding the button down. We can move around any part. Right click and hold it down, you can kind of pivot it. Don't forget, I told you had to go straight up and to the right, so it's going to have to go in that position right there. So we're going to do two mates here. One of them is concentric, so the holes line up, and the other is coincident, so that that surface right there and this surface right here are touching. It assumes that's what we want, so it just makes that the default. If that's what we want, we just do this, and now they all always touch. Now we can still move this around. You notice physics doesn't apply here. Now you can put it close if you want, but it doesn't really matter. Pick the inside of the hole, the inside of that hole, and now concentric is the most likely, and so that's the one that it uses. And now you have a lever that's only going to pivot that way, and then you have this, and the only thing we need to do now is to connect them with that tie rod. You get that far and you'll be able to make this work. You don't have to put both tie rods in, and you don't have to put that pin in because the holes themselves are always going to be concentric. So if we take the tie rod, call it a rod, it's actually a plate, but it's a tie, and I say take that surface right there and also this surface right here and put them together coincidentally. It looks like that. Now let's take the inside surface of that hole and the inside surface of that hole and make them concentric. Now let's make that hole and that hole also concentric, and that's all you need to do in order to make this thing work the way it's intended to work. Look at it from the front now. Looks like this. Push it that way, the piston goes out. Do this way, piston comes in. Now it will not automatically stop here. I had to go through and do a number of things to make that happen, but we don't have time to go through all of that on this. It's actually a project I do in my class. If you're really interested in learning SolidWorks, you might want to sign up for the class we teach, because right now it'll go all the way through. So, but you can see though, it does behave in a real-world fashion except for going all the way through. Possible to go to the Move tool. If you go to the Move tool, which is right here, you say I want to move this thing, and I want to do a collision detection, and then I want it to stop at collision. Now when I move that down, it's going to stop right there, and you may have heard that sound that it made as it clunked. So we can put that in place, and then we can constrain how it moves, and that's how we can actually check to see if this thing's going to work. But you can see actually without even doing anything else, if I were to push on this, it's going to get pushed into the base. Obviously then it wouldn't happen in real life. So it does work. I go back and do the same thing, move components, collision detection, stop at collision. I come over here now and bring that down, and it stops as soon as it hits here. And again, I'm pulling on this, so I know if I grab that and pull it, it's going to try to go through the base, which it can't do. And that happens sometimes if you pull on that too hard. It just kind of, rearranges things in a weird little way. So we can fix that by coming back out with it sometimes, and sometimes you got to go back and do it all again. That's just a weird little SolidWorks thing. Yeah, I'm not going to be able to fix it on this because of the way it's set up. So I literally have to go through and take it apart and do it again. So just don't grab it and do anything too dramatic with it because it'll do something that's impossible. That is everything that I would hope to be able to get done with you in 4 hours. So the rest of this, don't worry about. But that does give you a pretty good idea. So just a quick review. If we get to parametric modeling now, right down here. Sorry, I didn't mean to go back so far. Extrusions, create a shape, push it through space. Revolve, create a shape, revolve it around an axis, and push it through space that way. A sweep, give me a shape, give me a path, make that shape move along a path and create a solid from it. Loft, start with one shape, go to a different shape, and you can do that as many times as you want. And again, the ship hull is one way to do that. Shell something that's solid by giving it a wall thickness, and then you can remove, before you do that, individual surfaces, so it looks like that. And combine allows you to do actually 3 kinds of things. One is to give you what's common to whatever overlaps. You could have 100 things overlapping, and it would tell you, it would give you whatever was common to all 100, wherever they overlap. You could also add things together this way, and then you could also subtract one thing from another this way. So this is a pretty good tool. After that, I went over the sheet metal part and showed you all the drawings and go through that process. And then we skipped this and went right to this. So that's how assemblies work. I'm going to call it quits on this video. And hope you enjoy this and have a lot of fun with it.